Welcome back to our IB Physics video series. This is the first video in IB Physics topic 4, waves, where we will be looking at oscillations and simple harmonic motion. Before watching this video, ensure you have watched our IB Physics topic 2 video series, where we introduce some important principles required for this video. A core concept in IB Physics is that of oscillations, which are the continual movement of an object around a fixed point, called its mean position. You are expected to know 5 more properties of oscillations: displacement, amplitude, wavelength, period, and frequency. The displacement of the object x is the distance of the particle from its mean position measured in meters. The amplitude of the oscillation, a, is the maximum or minimum displacement of the particle, also measured in meters. The length of one oscillation is visible from crest to crest, or trough to trough, and can be defined by 3 terms: wavelength, period, and frequency. Wavelength, lambda, is defined as the length of one oscillation, measured in meters. Period, t, is defined as the time it takes to complete one oscillation, measured in seconds, and frequency, f, is defined as the number of oscillations that occur in 1 second, measured in hertz. It is worth noting that frequency and period are related by the formula period equals 1 divided by frequency. In addition, waves with a constant frequency or period are termed periodic, whilst those with multiple frequencies or periods are termed aperiodic. So how are 2 oscillations compared? The IB expects you to only compare 2 waves with the same frequency. Under this condition, they are compared by their alignment, termed the phase difference. This is measured in degrees or radians. But why is this the case? Well, since an oscillation looks like a sine or cosine function, you can think of one period being a 360-degree rotation. So, translating these degrees to the alignment of waves, we can see that a phase difference of 0 or 360 means that the 2 oscillations are aligned, termed in phase. A phase difference of between 0 and 360 means that the 2 oscillations are not aligned, termed out of phase. However, a special scenario occurs where there is a phase difference of 180. The waves are complete reflections of one another, termed perfectly out of phase. However, because period and wavelength are related, phase difference can also be described in terms of wavelength, called the path difference, p. Here, n is the order of interference, i.e. the number of whole wavelengths that make up the path difference. So, in-phase oscillations have a path difference of n wavelengths, and perfectly out-of-phase oscillations have a path difference of n plus a half wavelengths. Consider the following 2 in-phase waves. Wave 1 is 2 wavelengths ahead of wave 2, so n equals 2, and the path difference is 2 lambda. Consider the following 2 out-of-phase waves. Wave 1 is 1.5 wavelengths ahead of wave 2, so n equals 1, and the path difference is 1.5 lambda. Using these terms, you will be able to describe and compare any oscillation in IB Physics. However, you are only expected to focus on periodic oscillations which exhibit simple harmonic motion. Simple harmonic motion is defined as the motion of an object where its acceleration is proportional to, and in the opposite direction of, displacement. This is mathematically described as the object's acceleration is proportional to its negative displacement. Some examples of simple harmonic motion include a pendulum, a mass spring system, and waves. There are 2 main conditions required for simple harmonic motion, which can be summarized as when the object is displaced from its mean position, a restoring force acts to restore the object to equilibrium, and the magnitude of the restoring force is proportional to the object's displacement. But what does this all mean? Well, let's take a look at an example of a spring to put this into context. Remember that during its motion, the spring will have a mean position, a maximum displacement, and a minimum displacement. Let's look at what happens at each position. The mean position occurs when the spring is at rest. Displacement left of this position is negative, and displacement right of this position is positive. If the spring was stretched to its maximum displacement, the leftward elastic force in the spring increases to try and restore the spring to its mean position. If you release the spring, it has zero velocity, and at this exact moment, the elastic force is at a maximum, giving the spring the maximum negative acceleration possible. As the spring moves left to its mean position, the elastic force continually decreases, as the displacement decreases. At the mean position, the elastic force is zero, so the mass has zero acceleration. However, the spring has reached its maximum negative velocity, and so momentum carries it further left. As the spring moves left to its minimum displacement, the rightward elastic force increases to try and restore the spring to its mean position, slowing the spring down. At minimum displacement, the spring has stopped and so has zero velocity. However, the rightward elastic force is at its maximum, and so the spring experiences maximum positive acceleration. As the spring moves right to its mean position once again, the elastic force decreases back to zero. Therefore, acceleration once again decreases to zero. Then again, once at its mean position, it has zero acceleration, but a maximum positive velocity, carrying it rightwards. As the spring returns to its maximum displacement, like previously, the leftward elastic force increases to try and restore the spring to its mean position, slowing the spring down. Now back at maximum displacement, the spring once again has zero velocity, maximum leftward elastic force, and maximum negative acceleration. The spring could repeat this motion in two ways. Perfectly, i.e. in the absence of friction, the spring would endlessly repeat this pattern of motion. Or damped, i.e. in the presence of friction, the spring repeats this pattern of motion with decreasing amplitude. It is important to note that damped motion is still considered simple harmonic motion because the frequency and wavelength stay the same over time. In your exam, the IB will often place a mass on this spring, at which point it is known as a mass spring system. You've now reached the end of the preview for this IB Science video. If you want to check out the full video, head over to our website and select a membership plan today.